And so now we're back from our break, and we explored the calculus approach. So the calculus approach here, unless you want to get into gradients and all that multivariable good stuff, we'll just do it for the k equals 1 case. So we look at the partial derivatives of the Euclidean norm of the residuals with respect to beta 0 and beta 1, setting that equal to 0. We solve to find our estimates, beta 0 hat, beta 1 hat. And along the way, actually, you can see that the sum of the residuals is 0, and the sum of xi times the residuals is also 0. These are called the normal equations and are important in what follows. So you get the formula that we derived above here, just following this text. So here's just like a intro stat type of a question. So here's some data and find the regression line. So we just plug and chug and we get this. I should say that on homework 6 you'll show an alternative formula for the regression line involving the correlation coefficient. Then I showed you how to do this in R, so I don't really have anything to say here. Maybe I will just mention that in this equation here, so regression coefficients is a vector, and so this bracket 1 is the first entry, so that's 1, and bracket 2 is the second one, that's 0.7. So we get 1 plus 3 times 0.7, right, which is 3.1. So you can graph the regression line this way. If you want to look at error bars, you can do that as well. So we need a little bit of machinery now. So we talk about random vectors. And we come to this main theorem here, theorem AB on page 573, which tells us that the variance of the beta hats is sigma squared x transpose x inverse. So this is a big result. It requires some straightforward matrix algebra machinery that provides zero insight, so I'm not going to go into it. But we're going to focus now on the simple case to see what that means for us. So the covariance matrix is sigma squared x transpose x inverse. So I've written out what that is here for the simple case. And the nice formulas that I get are highlighted here. And the only one that requires a little bit of work is the one in red here, but Uncle Adam has worked out for you the details of how to derive that. So next, so these things all involve a sigma squared, but Tyche knows what sigma squared is. We don't, so we need to estimate it. Now, your book essentially says, okay, we're going to do this in the multivariable case, and they introduce a lot of linear algebra machinery to do this, and it doesn't shed a lot of light, and unless you're a linear algebra pro, it probably is not going to be that helpful. So instead, we're just going to go through it, but we're going to do it for the k equals 1 case, and hopefully you can see what's behind this. So we define the residual sum of squares, which is just the Euclidean norm of the residual vector, and this is going to be involved with our estimator. So now we're going to normalize our data, and this is not going to affect our estimator in any way. By normalizing our data so that x bar is 0, that's what I mean by normalizing it. Essentially, we can subtract all of our x's by x bar. That would have the effect of making the mean 0. And so what that's going to do, as I showed in this picture, is it's basically going to translate all of your data, the orange here. It's going to translate all your data such that it's centered now at its x value is centered at 0 instead of centered at x bar, right? X bar is essentially becoming 0, and that will just translate the Tyche line and the regression line. It'll just translate that over. So the errors and the residuals are going to be what they were before. So now we're going to show that the regression sum of squares, I forgot a square here, the regression sum of squares over sigma squared is a chi-squared with n minus 2 degrees of freedom. So that's a key result. To show this, we're first going to show that the sum of squares of the errors over sigma squared is actually chi-squared with n degrees of freedom. So to do this, let's just take a look at the sum of squares of the errors, and we do some trick here where we add and subtract beta 0 hat and beta 1 hat xi, and we group it and we square, and then here we see that the AB, AC, BC are all 0 because of x bar being 0, which is something we're assuming now, and then our normal equations. So having all of this makes things very nice. So we don't have any of these cross terms anymore, and our sum of squares, error over sigma squared, now has 3 terms. And I just wanted to point out that beta 0 hat and beta 1 hat are normal, with mean and variance shown here. Remember that x bar is 0, so that's why for beta 0 hat the variance is sigma squared over n. There was another term here that involved an x bar, but that was 0. So we're essentially normalizing the beta 0, we're standardizing the beta 0 hats, so we get basically z squared, another z squared, and then here we have RSS over sigma squared. Furthermore, these chi-squared 1 degree of freedoms guys here are independent, so their sum is chi-squared 2 degrees of freedom, and it then follows that RSS over sigma squared is chi-squared n minus 2 degrees of freedom. Wow, good job. That is a really big result. So now we can say that RSS has n minus 2 degrees of freedom, and we know lots about chi-square distributions. In particular, the expectation of chi-squared with n minus 2 degrees of freedom is n minus 2, so the expectation of RSS over sigma squared is n minus 2, and it follows from that that RSS over n minus 2 is an unbiased estimator of sigma squared. Wow, that is so awesome. So now we have our estimator, and we can then find confidence intervals for beta 0 and beta 1, and that's what we concluded with today, and this was very easy. So if you remember what a t-distribution is, t with n degrees of freedom is a ratio of standard normal by square root of a chi-squared with n degrees of freedom over n. And so now my z is going to be, so if I want the standard error for beta 1 hat, my z is going to be beta 1 hat minus beta 1 over its standard error. And u is going to be this chi-squared. And so then Tn minus 2 is what's given here. And so this denominator here we call the approximate standard error, right, for your beta 1 hat. And that's awesome. And so that allows us to get a 95% CI, for example, for beta 1. And you can do the same thing for beta 0.